Hey, welcome back. We want to go from the last section. We couldn't really find solutions, but we were able to kind of approximate the solutions visually to this section where we're going to give you techniques for actually finding the solutions. Okay, so the method we'll be using separation by separation of variables, but they do introduce you with just using integration. So first we start with solution by integration. Whoops. So this is kind of in the same class as the separation of variables. It's just on the right-hand side of your differential equation, you have something that's completely only dependent on x. And in those cases, you could go ahead and solve just by integrating. So you look in the book, their first example, where are you? They have dy all over dx equals 1 plus e to the 2x. Okay, so all you need to do is just integrate that right-hand side. You get 1 plus e to the 2x dx. And of course, the integral of 1 is x. The integral v of the 2x is e to the 2x all over 2. And then plus your constant of integration, c. Okay, so the deal with this guy, its right-hand side is a function of x only. When you're dealing with separation of variables, on the right-hand side, you'll have a product, a function in terms of x, and then a function in terms of y. Okay, usually. You know, we're going to see examples where it looks really kind of like mixed up, but you're able to kind of pull this off. You're not always able to separate. That's one of the first things they even note here in definition 2.21 here in the book. You're not always going to be able to separate. So not always, I'll just write star, not always possible. Possible to do this. Okay, and if that's the case, you'd have to find a different method. But when you have the form dy over dx equals some function of x times some function of y, we'll be able to pull this off. First thing to note, which is a common theme throughout this section as you read, you have to watch out for accidentally losing solutions when you divide by this h of y function. Because if h of y is equal to 0, it will be a solution to this differential equation. But when you divide by h of y, you've presumed that that is not the case. Okay, so let me just note, first off, if h of y sub 0 equals 0 for some y sub 0, then y equals y sub 0 will be a solution. Okay, and as you read through the section, there's an example where you lose two solutions. One you can still obtain from the general solution, but then the other one is kind of a singular solution that you can't get your hands on. Yeah, that's this example right here. You're probably reading through that. That's the example we've seen before. Okay. So they will bring that up again and again throughout the section. You know, you're going to lose a solution. There's another example. Losing solutions. Okay. Once you've dealt with that issue, then go ahead and get all the y stuff on one side, all the x stuff on the other, which, in other words, separate. Then you're going to integrate both sides. And then you're going to try to get an explicit solution, which may or may not be possible. Try to get explicit solution. All right. So let's take a look at, I guess, their first example. They do this whole thing where they're basically looking at the problem in generalities with abstract functions. But let's go ahead and dive into their first example. So example 1. And they give the problem in the differential form. So it doesn't even look like a separable equation, but it is. Okay, so what I'm going to do is divide through by dx. So I get 1 plus x dy over dx. minus y is 0. Then I'm going to try to isolate the dy over dx. So add y to the other side. And basically what I'm doing is separating. Okay. Then I'm going to divide both sides by 1 plus x. And I guess it wasn't even necessary for me to kind of try to put it in the dy equals, the dy over dx form. I didn't even really need to do that. But okay, so let me move the y to the left side, so I get 1 over y dy over dx, and on the right side I got 1 plus x. So what they're not going to show you in the book is technically you're integrating right here both sides with respect to x. Okay, on both sides of the equation you're doing dx. What they do in practice, though, instead of having to write all that out, is just move the dx to the other side without the dy. So you'd end up with 1 plus x. You would end up with 1 over y dy. And on the other side, you're going to get 1 over 1 plus x dx. Okay. But again, technically, you're leaving that dy over dx on the left and integrating both sides with respect to x. So this is kind of like in my brain, I wouldn't ever write that out, but that's technically what I'm doing. And you won't see that thing I just did in red in the book. They just kind of skipped that. Okay. So anyways, once I've literally moved all the y stuff to one side, all the x stuff to the other, then I'm going to integrate both sides. I get the ln of the absolute value of y here. On the right, I get the ln of the absolute value of 1 plus x, and then plus constant. And again, here there's some details that they're kind of shoving under the rug, and that detail is that technically, again, there's a constant on both sides. So there'd be a c1 here, and on the other side, ln absolute value 1 plus x plus c2. But what they've done is combined both the constants on one side into one big constant. That's the c value here. Okay. There's no reason to keep track of all the individual C1s and C2s. At the end of the day, you can solve for C1s and C2s and all that jazz as long as you know the initial conditions. Okay, so anyways, once we have this form, let me move this back over here, then we can exponentiate both sides to get an explicit solution. Okay. So right now it's implicit. We're not happy with that form, though. We can do better. Okay. So here we are. When the e and the ln are kind of touching like this, they're inverse functions. They will annihilate each other, so you end up with the absolute value of y. On the right-hand side, the e and the ln kind of cancel each other out. You got to be careful about that plus c. You want to rewrite it as e ln absolute value 1 plus x times e to the c. And that's just the, probably, I forget what they call it. It's this rule, a to the x times a to the y equals a to the x plus y. Right? It's that rule, but in reverse. So we started like on this side and kind of went over to this side in this step here. Anyways, I'm going to rewrite it with e to the c in front. So I have e to the c times e to the ln. Again, the e and the ln will kind of cancel each other out. You just have the absolute value of 1 plus x. Then you could drop all the absolute values and replace it with a plus or minus. And then you could replace this whole thing with a constant c, where c represents any real number, including 0, because at the beginning, if you did not notice, 0 is a solution. Okay, it would work. So you could write y equals c times 1 plus x. Okay, a lot of weird kind of small details going on, but once you get the hang of it, it's like riding a bike. It's no big deal. One other issue the book notes is right here. You could write the constant on the right-hand side as an ln. Basically, the constant just represents any real number, and because of the range of ln of c is all real numbers, you could use that in place of c. And the advantage would be that because we're dealing with natural logs, we can rewrite automatically the ln of 1 plus x times the ln of c as c times absolute value 1 plus x. Okay, so we could use the product rule to rewrite it as, I think I want to move my absolute value, my product rule as c times the absolute value 1 plus x. Okay, that can make life a little easier. Honestly, I haven't used it. It only comes up in, and I guess they're using absolute value of c. It only comes up in when I look at my answer solution keys. It seems like that's the only place that I ever really see it. So I wouldn't worry too much about it. But in case you do see it and you're wondering what the heck they did, it's that. Okay, you can use ln c instead of just plain old. And that kind of defies my whole idea that you could use ln. We're using ln of absolute value of c. And that seems like it's not a good choice because you wouldn't get any real number as a possible output. Because you would never have, well, you can never put a negative inside the ln, so that works. Okay, but not a big deal. We don't need to worry too much about it. Okay, so anyways, let's look at some more sort of examples from maybe the book here, or even WebAssign here. So number 3, I guess, or maybe even number 4. We got dy over dx equals e to the 3x plus 5y. Excuse me. We could rewrite this as dy over dx equals e to the 3x times e to the 5y. Then I can move all the x stuff to one side, all the y stuff to the other. So I get e to the negative 5y dy, and over here e to the 3x dx. And then you can integrate both sides. This one's pretty standard type problem. E to the negative 5y over negative 5. Over here, e to the 3x over 3 plus a constant. For whatever reasons, you can kind of get rid of the fractions by multiplying by 15. So you'd end up with negative 3e to the negative 5y equals 5e to the 3x. And then this constant c will absorb other constants. So I mean, normally you'd have 15c, but you can just replace that with a c. And then you can move the 5e to the 3x to the other side if you'd like. So I have 5e to the 3x, then minus 3e to the negative 5y. Actually, it would be minus if you pull it over there, and then equals c. And then you could, if you want to, multiply both sides by negative. And that's what I have as my solution. I kind of write it that way, not for, I mean, this is a fine solution. If you put that on a test, I'd be fine with that. Just for whatever reason, this one looks better. Sometimes it's just a matter of what you're familiar with. So if you work a lot with certain cubic functions, I guess that come up in algebraic cryptology, that would be the form you were used to, and you would hope that all your answers were in that form, and you would kind of push them into that form. That's kind of what I'm doing here. It's like I'm more familiar with this last circled form, but you as a student are probably not familiar with all that many forms, and you'd probably just stop right there, right? So you can if you want to, and I'm sure the computer would be okay with that answer. Let's look at another one here, number 5. This one looks like a nightmare. I'll go ahead and rewrite this a little bit. First off, it's dx over dy here, so I'm going to rewrite it as dy over dx just so it's more familiar to me. And again, you got to move all your y stuff to one side, all your x stuff to the other. So anyways, Looks like I'm getting y. Y plus 1 squared all over y times dy equals, on the other side, it just seems like x squared ln x dx. Okay. Then you got to integrate both sides. On the left, you can FOIL out the top, and that would make your integration day easier. On the right, it looks like you're going to have to do by parts. So all that junk you learned in Calc 2 is, applies here. So u and dv, u is the ln x, dv is that x squared, and then v will be x cubed over 3, du will be 1 over x dx. Okay. Then it's u times v, so x cubed ln x all over 3 minus v du, the integral of v du. So there's a factor of 1/3 I could pull out, and then I'll have x squared dx. Rewriting the integral on the left, 1 plus 2, this should be a y squared, y plus 2 plus 1 over y dy. And then on the right, x cubed ln x over 3 minus 1/3 x cubed all over 3 plus c. Integrating y squared over 2 plus 2y plus ln absolute value y. And on the right, x cubed ln x over 3 minus x cubed all over 9 plus c. You can multiply through, by like 36 or something to get rid of all the fractions. But literally, I got sick of it, and I just typed it in as is, and that's the answer. This brings us to the point that you're not always going to be able to get this nice y equals solution. You're not always able to get these explicit solutions. So here, no. Down here, no. Here, the first one, yeah, I could get this is explicit, right? But these other guys aren't. This is not explicit, it's implicit. And likewise, this guy down here is implicit. But you could still graph these things. I think that in the book, they say you have to use like level curves and stuff, but the truth is, I don't think the guy who wrote our book has left the house in 50 years because he's so out of touch. He has to be like 100 years old at this point, the guy who wrote the book. But I'm sure you could go to Desmos and graph this thing, and you don't need to necessarily put in the plus c part. You could get it for particular, anyways, plus ln of the absolute value of y equals x cubed ln x, ln of x all over 3 minus, I shouldn't say about that guy who wrote the book. I'm sure he's an awesome dude and all. Let's say plus 5 or something. Is it not gonna? It's not gonna even let me do that. Well, I stand corrected then. What's wrong with it? You need arguments. You don't like the absolute value. I guess not. So it gives us something, It just looks like half of a parabola. But you could kind of go and see what it looks like is maybe my point, right? Like the book will say, well, you're not going to be able to graph it, and you have to go to the computer, and that's what they're talking about right here is graphing level curves. So what you do is just take your solution and set it equal to the constant, and then let the constant equal whatever you want, and pretty much graph those things, and you get an idea of what it looks like. Okay. All right. Then the next section, then once you get your stomach, maybe we should look at this example 3 Here's a solution curve. Intervals of definition are still in play for us. Let's look at losing a solution, example 3. So we have dy all over dx is y squared minus 4. I have dy then all over y squared minus 4 equals dx. And that's going to be on the left. It's you got to do a partial fractions, right? So y squared minus 4 is y minus 2 times y plus 2. And there's also the issue of losing a solution here. So when you've divided by y squared minus 4, you assume that y is not equal to 2 or negative 2. Okay, those are solutions. So note this y squared minus 4, where that equals 0, that gives you solutions. Okay, for y is plus or minus 2. So those are two constant solutions. Anyways, let's go back over here and do our partial fraction decomposition. Multiply through to get rid of the denominators. Sub in y is negative 2, so you get 1 equals negative 4b. So b is negative 1/4. Let y equal 2. So 1 equals 4a. So a is 1/4. So what do we have then? Our left-hand side becomes the integral of 1/4 all over y minus 2 minus 1/4 over y plus 2. On the right-hand side, dy. On the right-hand side, we have x plus c. So this will be 1/4 ln absolute value y minus 2 minus 1/4 ln absolute value y plus 2 equals x plus c. You can multiply through by 4. That gives me ln y minus 2 minus ln y plus 4, or sorry, y plus 2 equals 4x plus the constant absorbs the 4. Then you could use the quotient rule for natural logs to rewrite this as y minus 2 over y plus 2 equals 4x plus c. Then we could try to get an explicit solution by exponentiating. Okay, so I get absolute value y minus 2 over y plus 2 equals e to the c times e to the 4x. Drop the absolute values. Get plus or minus e to the c, e to the 4x. And y minus 2 is c e to the 4x times y plus 2. I'm going to try to track down an explicit solution. Y minus 2 equals c e to the 4x y plus 2c e to the 4x. Move this guy over, and then the negative 2 over here, add 2 to the other side, so y minus c e to the 4x, which should become y plus c to the 4x if you wish, equals 2c e to the 4x plus 2. Whoops, I lose the y somewhere. You can factor out the y, so you get 1 minus c e to the 4x equals 2c e to the 4x plus 2. So y would equal finally 2c e to the 4x plus 2 all over 1 minus c e to the 4x. Let's see if I'm even close. Yeah. And then just you can factor out that, I guess they're going to factor out the constant in the numerator. 2 c e to the 4x plus 1. Then 1 minus c e to the 4x. I'm not going to let the constant be absorbing the 2 or the negative, because it kind of seems like then I'd have two different constants I'd have to worry about. So I'm going to leave it like that. Note in this form, it would not be possible to get the solution of, so if you let c equal 0, you would get y equals 2 as your solution, as a solution, but there's no way to get the negative 2 out of it. It's just not going to pan out. And so y equals negative 2 is a singular solution, but y equals 2 is from the family. Okay? So it's a bit weird. That's what they're going on about in this problem. Anyways, from there we look at initial value problems. So let me introduce another section here, section 2, initial value problems. And basically it's the same thing, except you can use the initial condition to find your particular solution in other words, to solve for your c, your constant c. So just use the initial condition to solve for your constant c. So I seem to have one there. Let's look at a different one from the homework, preferably. Where they give us an initial condition. There's an initial condition somewhere. Here's one. So this guy. Number 12. I have dx over dt equals 6 times x squared plus 1, and the initial condition x of pi over 4 equals 1. Okay, so separate first. Got dx all over x squared plus 1. The other side 6 dt. And then it looks like we can integrate both sides. The integral of 1 over x squared plus 1 is tan inverse arctan, if you wish, of x. The other side I have 6t plus c. And now you just use the initial condition here, up here, to solve for c. So plugging in 1 for x, I get tan inverse of 1 on the other side. Pi over 4 for t, 4 plus c. Tan of 1 is pi over 4. 3 pi over 2 plus c. Move this 3 pi over 2 the other side, so pi over 4 minus 6 pi over 4 basically is negative 5 pi over 4. And then we'll have tan inverse of x equaling 6t minus 5 pi over 4. If you look at the way they have their solution, they want it solved for x. So all you need to do is take the tangent of both sides to undo the tan inverse. So basically you have tan of tan inverse on one side, and then you have tan of 6t minus 5 pi over 4. So that will be x equals tan of 6t minus 5 pi over 4. Okay. Right, so there's that, particular solutions. Let's maybe look at, I guess, an example. So in the homework, they don't really focus too much on the interval of definition or anything like that. Back in the day, when you actually did the homework from the book, you would have seen problems like that. We're not going to actually see those in the homework, though, so I'm going to just kind of leave that out. So basically, you have to pick the interval of definition from where your initial condition is. So if you're defining, well, maybe I should go through it. If you want to see it, you can look at it. If not, you can kind of skip ahead, skip through this exercise. So anyways, an example, dy over dx equals 2x plus 1 over 2y. And then we want y of negative 2 equals negative 1. So separating integrating, and then here we have an implicit solution. The explicit solutions would be you'd find by taking the square root on both sides, and you get x squared plus x plus c inside of that square root. For our initial condition, we require y to equal -1. So the solution we would want would be the y equals negative square root x squared plus x plus c. And then on top of that, there are, issues with the continuity of this thing. Let's get use the initial condition to get the particular solution. So if we let y equal -1, on this side we've got negative square root of 4 minus 2 plus c, and so -1 equals negative square root of 2 plus c, square both sides, you get 1 equals 2 plus c, so c is -1, right? So our particular solution looks like y equals negative square root of x squared plus x minus 1. There's an issue here though, right? Because the interval definition is what? Well, I need x squared plus x minus 1 to be greater than 0, greater than or equal to 0. And likewise, you need that to work. You also need to worry about the derivative as well. So the derivative would be like 2x plus 1, and there's a negative floating around. From the chain rule, you get the 2x plus 1, and then you get the x squared plus x minus 1 to the 1/2 down here. So you wouldn't be allowed to use the equals because the derivative would have an issue there. But we need to make sure this works. Sort of the boundary points where it would equal 0, use the quadratic, you get negative b plus or minus the square root, so -1, sorry, -1 plus or minus the square root of b squared minus 4ac, so 4 times 1 times -1 all over 2. That'd be -1 plus or minus c square root of 1 plus 4 is 5 all over 2. Okay, so we can kind of look at a number line and see where that thing works as being greater than 0. So -1 minus square root 5 all over 2, -1 plus square root 5 all over 2. If you bother, the sign will be positive, negative, and then positive here for that parabola. So at the end of the day, our interval of definition has to be either negative infinity to -1 minus root 5 over 2, or -1 plus root 5 over 2 to infinity. Given our initial condition of y of -2, we have to be then in this, I believe will be in the left side interval, right, this over here, because that's where the x value is from our initial condition. X is -2. So our interval of definition would be negative infinity to -1 minus root 5 over 2. Okay. But like I said, they don't really do that in the homework. They don't really seem to care. So it's not going to be an issue for you. The last thing we need to worry about is what happens when I can't integrate. So section 3, basically you'll have a solution defined by an integral. Defined by an integral. And let's see. Integral, yeah. So when you have so let's look at, so you're going to be given some dy over dx equals some function of x usually, and some initial condition. You can write up the solution as y equals y sub 0 plus the integral from x sub 0 to x of g of t dt. And all that means is basically on the right-hand side, you weren't able to integrate, okay? But you could still kind of embed the initial condition into your answer. So in example 5, Let's take a look at that guy. dy over dx equals e to the negative x squared, and then our initial condition, y of 3 is 5. So you could kind of approach it like you normally would by separating, but you're not going to be able to integrate that right-hand side. Okay? But you can kind of, I don't know, embed the limits into the integrals. So here you would go from 3 to x, and also here. So the antiderivative y from 3 to x, and over here you just don't know. Technically you need to use like a dummy variable inside the integral like t. So let's put a t in there. Okay. So you would have the integral from 3 to x of e to negative t squared dt. And on the right-hand side, you have y of x minus y of 3 equals the integral of 3 to x e to the negative t squared dt. And that's pretty much it. You can move the y of 3 over plus the integral from 3 to x of e to the negative t squared dt. Okay. You could use this method to avoid that back substitution at the end when you're solving for c. You can always embed the initial conditions into the integral. So for instance, I guess we don't have a nice one here. Maybe that one turns into a monster. Maybe let's look at an easy one right here. It's not very easy. None of them are very easy. So let's see if we could pull off the answer for number 14 by embedding the limits in the integral, the initial values into the limit of the integral. Square root 1 minus x squared dy equals 0. Y of 0 is square root of 2 over 2. So here I go. The square root of 1 minus y squared dx equals square root 1 minus x squared dy. Separate, so I'm going to put dy all over square root 1 minus y squared. And then on the other side, 1 all over square root of 1 minus x squared dx. And then I want to integrate on both sides, but I'm going to kind of embed the initial conditions. So 0 to x as well as 0 to x over here, but technically we have to change this to a t, okay, if you allow me to. Then you can integrate, so over here it's sine inverse of y from 0 to x, and on the right hand side we have sine inverse of t from 0 to x. It should be noted that y, this function y over here, is a function of x. Okay, so if you want to help, you can put a little x in here. That may help, maybe not. So anyways, you'll have sine inverse of y of x minus sine inverse of y of 0. On the right-hand side, you'd have sine inverse of x minus sine inverse of 0. And then sine inverse of y of x minus sine inverse y of 0 is given as root 2 over 2. On the right-hand side, you have sine inverse of x. Sine inverse of 0 is just 0. Okay. So we have sine inverse of y of x equals sine inverse of root 2 over 2 is going to be pi over 4. And then if I add that to the other side, I get pi over 4 plus sine inverse of x. And then just take sine on both sides to get rid of the sine inverse and get y of x equals sine of pi over 4 plus sine inverse of x. So it's just another way you can go about avoiding the plus c and then having the back sub and solving for the c if you want to. Okay, so I see that every once in a while when I'm having to do research. Not that I do a lot of research, but yeah. And then if there's something you can't integrate, you just leave it as an integral. Okay, so I think that pretty much does it. Pretty much says all I want to say about that. I'll do one more example. You can watch it. You don't have to. Well, no, let's make this one the video quiz. So number 10 is the video quiz. We got dy all over dx equals xy plus 7x minus y minus 7 all over xy minus 2x plus 8y minus 16. So this is a trick. If you don't see it, you might be stuck. And it's grouping, right? So the first two terms you could factor out an x and you get y plus 7. Next two terms you can factor out a negative. On the bottom you can factor out an x and then factor out an 8. And then you get a function of x times a function of y, basically. So x minus y times x plus 7. You factor out the common binomial of x plus y plus 7. Maybe I should write the other way around. It's more obvious. And downstairs, we factor out the common binomial of y minus 2. You end up with that. And then you could separate. So on the y side, you'll have y minus 2 over y plus 7 dy. On the x side, x minus 1 over x plus 8 dx. And then you can integrate. Trick you can do is let u equal y plus 7. And then du is just dy. And then y minus 2 is equal to, what, u minus 9? Right, so if I subtract the 7 over and then subtract 2 from both sides. And then on the other side, I'll let u equal x plus 8. So du is just dx. And then x minus 1 equals, so u minus 9 again. Okay. And then I can integrate, so I'll have u minus 9 all over u du equals the integral. Let's use a different letter than u. So I'll have z minus 9 all over z dz, if these guys were all z's. And then I can butterfly those, so 1 minus 9 over u du. Over here, 1 minus 9 over z dz. And then I integrate, so I would get u minus 9 ln absolute value of u equals z minus 9 ln absolute value of z. Let's see, and then back sub u is y plus 7. So y plus 7 minus 9 ln absolute value, y plus 7 absolute value equals z, which is x plus 8 minus 9 ln absolute value, x plus 8, and then plus c. Okay? And that'll do it. So let's leave it at that. Thank you for watching as usual, and I will see you next time.